Welcome back to The Explainer. Today, we've got a truly fascinating blueprint to decode together. We're looking at the complex, yet absolutely necessary leap from traditional computing over to brain-inspired neuromorphic systems. So let's dive right in and find out exactly where hardware is heading. Stop being a mere instructor for LLMs and start becoming a neuromorphic architect before the industry leaves you behind. That is a massive wake-up call. Traditional programming architectures are literally hitting a wall right now, and mastering synaptic-based logic is rapidly becoming vital for anyone who wants to build the next generation of autonomous systems. Here is our blueprint for today. We'll cover 1. The AI memory wall, 2. Biological logic, spiking networks, 3. Memristors and in-memory computing, 4. Hardware evaluation with SpikeSim, and finally, 5. Building the software bridge. Let's start with Section 1, the AI memory wall. To really understand this shift, we have to contrast traditional AI with neuromorphic AI. You see, traditional systems use the classic von Neumann architecture, which completely separates the memory from the computation. This creates massive energy and latency costs just from constantly shuttling data back and forth, resulting in a huge always-on waste of energy. Neuromorphic systems, on the other hand, co-locate memory and compute. They're asynchronous, they're event-driven, and they elegantly process data only when it actually changes, exactly like a biological brain. Moving to Section 2, biological logic, spiking networks. The algorithmic solution to breaking down that memory wall lies in spiking neural networks, or SNNs. Now, unlike the continuous signals you see in standard deep learning, SNNs process information using discrete, binary spikes over multiple time steps. Think of it more like tapping out Morse code rather than broadcasting a continuous radio wave. Because computation literally only happens when a spike fires, the energy savings are absolutely incredible. Next up, Section 3, Memristors and in-memory computing. Of course, algorithms are only half the battle. We also need the physical hardware to run them. At the physical level, we're talking about a computing and memory architecture using a memristor crossbar array. These memristors act just like physical human synapses, storing data as actual physical resistance. And by putting memory right inside the computation layer, we completely eliminate that massive bandwidth bottleneck of vector matrix multiplication. So, if you're wondering how to actually apply this technology, let's walk through the detailed instruction set for computing on a memristive layer. Step 1. You map your input vectors as physical voltages on the horizontal word lines. Step 2. Map your weight matrices as conductance values directly into the crossbar. And Step 3. You just let physics do the math in the analog domain and efficiently accumulate the output currents from the vertical bit lines. It's a brilliantly simple application of physics. And the best part? These aren't just theoretical diagrams anymore. We now have actual photorealistic captures of a fabricated memristor crossbar under microscope probes in a lab. We are looking at physical, nanoscale synthetic synapses, which proves for sure that this architecture can be built using modern, compatible manufacturing processes. But the absolutely crucial takeaway here is this specific number, 2.51 picojoules. That is the shockingly low energy cost per synaptic connection on these fabricated memristors. When your system is processing billions of parameters, dropping energy costs down to single-digit picojoules changes the entire landscape for AI accelerators. To really grasp the viability of this tech, let's look at some exact measurements. On a standard recognition task, this 65-nanometer analog cell architecture consumed just 2.9 milliwatts of power, hitting incredible inference speeds of 2 microseconds per image. Add in a highly stable cycle-to-cycle variation of just 4%, and you've got an incredibly efficient, highly reliable system ready for real-world deployment. That brings us to Section 4, Hardware Evaluation with SpikeSim. Now, evaluating this kind of analog hardware is notoriously difficult. Prior tools, which were largely designed for traditional networks, simply overlooked the non-ideal realities of analog crossbars. That's exactly why researchers had to build SpikeSim. It's an end-to-end tool specifically designed to realistically benchmark the performance, the latency, and the physical area of these in-memory computing SNNs. And when engineers actually ran SpikeSim, they uncovered a massive hidden cost. It turns out the leaky integrate and fire, or LIF neuronal module, can consume up to 30% of the entire chip area. Why is that? Well, because unlike standard networks, SNN neurons act sort of like little buckets holding water. They have to physically store membrane potentials between time steps before they can spike. That requires physical SRAM memory, which is a huge area overhead that older tools completely missed. Fortunately, SpikeSim gives engineers a direct blueprint to fix it. Evaluations showed that making some simple SNN topological modifications, like specifically reducing the output channels in the first convolutional layer, drastically improves efficiency. That single tweak shrinks the neuronal module area by 1.24 times, and it delivers a massive 10x improvement in the overall energy delay product. Finally, Section 5, Building the Software Bridge. So, despite all these incredible hardware metrics, widespread commercialization is still lagging. The reason? Well, the neuromorphic deployment gap is primarily a software and ecosystem problem. Developers are essentially required to learn an entirely new, event-driven programming paradigm. Plus, the global talent pool for this is incredibly small compared to the millions of devs who already know PyTorch or CUDA. To help bridge this gap, the industry is relying on robust new ecosystems like the Intel Lava framework. Lava is an open-source framework for neuro-inspired applications that beautifully blends a familiar, simple Python interface with underlying C, C++, and CUDA for accelerated performance. By using event-based message passing, developers can easily map these complex processes onto heterogeneous execution platforms. This means you can prototype on conventional CPUs and GPUs, support offline backprop-based training, and then deploy it straight to the edge. So we've covered the memory wall, the spiking biological logic, the physical memristors, and the software ecosystem needed to run it all. You are now holding the literal blueprint for the next era of industrial AI. The only question left is, what autonomous systems will you build with your new synthetic synapses? Subscribe to AI Vanguard AI to stay at the cutting edge of industrial AI. If you found this synthesis valuable, please like, comment, and share. Thank you so much for joining me on this explainer today, and I absolutely can't wait to decode the next major technological leap with you very soon.